Hello there, and welcome to Simple Sleepy Science. Have you ever noticed how the sound of distant thunder can make you feel safer than silence itself? While most of the world runs for cover when storms approach, something ancient in our biology whispers that we should stay still, rest, and let the sky do its work. Tonight, we're going to discover why thunder might be the most underrated lullaby nature ever created. Before we begin this journey into the peaceful world of thunder, please take a moment to like and subscribe so you don't miss more amazing stories tomorrow. And leave a comment telling us where you're watching from and what time it is there. We love hearing from our global community. Thunder is the voice of the sky, and it has been speaking to humans since the very beginning. But here's what makes it special. Unlike almost every other loud sound in nature, thunder doesn't signal danger to your body. Your ancestors knew this. When they heard thunder, they didn't run. They found shelter, gathered close, and waited. The sound told them that rain was coming, that the dry season might be ending, that the crops would grow. Thunder meant survival, abundance, and rest. Think about what thunder actually represents. It's the sound of the atmosphere balancing itself, of electrical charges finding equilibrium, of nature solving an equation that was temporarily out of sync. Every rumble is the sky saying, everything is being put back in order. There's something deeply comforting about that on a subconscious level. Your nervous system hears thunder and recognizes it as the soundtrack to natural processes that have sustained life on Earth for billions of years. We've somehow forgotten this ancient relationship with storms. Modern life has trained us to fear inconvenience more than we appreciate natural phenomena. A storm means cancelled plans, traffic delays, potential power outages. But strip away the modern context, and thunder is simply air molecules colliding, creating pressure waves that massage your eardrums in surprisingly rhythmic patterns. It's percussion without malice, power without threat. The frequency of thunder falls mostly in the range that humans find naturally soothing. It's low enough to feel in your chest, creating a gentle vibration that mimics the heartbeat you heard in the womb. It's irregular enough to prevent your brain from tuning it out completely, but predictable enough that it doesn't spike your anxiety. Thunder occupies this perfect middle ground where your mind stays engaged enough to avoid racing thoughts, but relaxed enough to let go of the day's tensions. Around the world, different cultures have always understood this. The Japanese have a word, natsukashi, that describes a nostalgic wistfulness, often triggered by summer thunderstorms. In parts of Africa, thunder is considered the sound of ancestors communicating, offering protection through the night. Nordic cultures speak of thunder as the gods working in their forge, creating the tools that keep the cosmos functioning. Every interpretation shares a common thread. Thunder is the sound of larger forces at work, forces that dwarf our daily worries and put our small concerns into peaceful perspective. When you hear thunder tonight, you're hearing the same sound that comforted your ancestors in caves, in huts, in ancient cities now turned to dust. The sound hasn't changed, and neither has its effect on the human nervous system. So what is thunder, really? Strip away the mythology and the fear, and you're left with something beautifully simple. Thunder is just air expanding, That's it. Air getting pushed out of the way so fast it creates a sound wave. But the story of how that happens is where things get interesting. Lightning heats the air around it to about 30,000 degrees Fahrenheit in less than a second. That's 5 times hotter than the surface of the sun. The air molecules don't have time to move aside gradually. They get shoved violently outward, creating a shock wave that ripples through the atmosphere. That shock wave is what your ears detect as thunder. Picture it like this. Imagine taking a metal rod and heating it gradually over a fire. The air around it warms slowly, rising gently upward. Now imagine dunking that same rod into a bucket of water while it's white hot. The water explodes into steam instantly, creating sound and motion. Lightning does the same thing to air, but with far more energy and far more speed. The channel that lightning creates, the actual path it burns through the sky, is only about an inch wide, sometimes less. All that sound, all that rolling boom you hear, comes from a column of superheated air no wider than your thumb. The lightning stretches for miles, branching and forking, and every inch of it produces its own thunder. But here's what makes it peaceful rather than jarring. The sound reaches you at different times. Sound travels at roughly 167 miles per hour through air at sea level. That might seem fast, but compared to light, which moves at 186,000 miles per second, sound is practically crawling. When lightning strikes a mile away, you see the flash instantly, but the sound takes about 5 seconds to reach you. If the lightning bolt is 3 miles long, stretching from cloud to ground with branches spreading sideways, different parts of that bolt are different distances from your ears. The thunder from the closest part arrives first, sharp and clear. Then comes the middle section, slightly softer. Finally, the rumble from the farthest parts reaches you, deep and rolling. Your brain processes all of these as one continuous sound, creating that characteristic rumble that can last for 10, 15, even 30 seconds. It's nature's way of stretching a single violent event into something gradual and soothing. This is why thunder never sounds like a simple crack, unless you're dangerously close to the strike. Distance transforms violence into music. The shockwave from each segment of lightning overlaps with the others, creating harmonics and resonances that are surprisingly complex. Scientists have analyzed thunder recordings and found patterns that resemble orchestral arrangements, complete with crescendos and decrescendos, bass notes, and higher frequencies all woven together. The atmosphere itself acts as an instrument. Temperature layers, humidity gradients, wind patterns, they all affect how thunder travels and transforms. Cold air bends sound waves differently than warm air. Mountains create echoes. Valleys channel the sound along specific paths. Every thunderstorm is unique, not just in where the lightning strikes, but in how the resulting sound reaches your ears. And your body knows this sound. It recognizes thunder as something that has echoed through every generation of human existence. A reminder that you're part of something ancient and ongoing. This brings us to why thunder rolls, instead of simply banging once and disappearing. The rolling quality is what makes thunder so perfect for sleep, and it happens because of geometry and distance working together in your favor. When lightning strikes, it rarely travels in a straight line. It branches like a tree, with a main trunk and dozens of smaller paths spreading outward. Some parts might be 2 miles away from you. Other parts might be 5 miles away. Still, others could be right overhead, just a few hundred feet up in the clouds. Each branch creates its own thunder, and each one has to travel a different distance to reach your ears. The sound from the nearest point hits you first. Let's say that's a sharp crack, the kind that makes you notice the storm. But while you're hearing that, the thunder from the parts farther away is still traveling toward you. It arrives a moment later, softer because distance has absorbed some of its energy. Then comes the thunder from even farther sections, quieter still, layer after layer of sound waves washing over you, each one slightly dimmer than the last. This creates what acousticians call a decay envelope. The sound starts strong, then gradually fades over several seconds. Your brain interprets this as a single continuous event, rather than multiple separate sounds. It's the same principle that makes a piano note feel smooth, even though it's actually the result of a hammer hitting strings, and those strings vibrating at different frequencies. But there's more to the rolling effect than just distance. The shape of the lightning bolt matters enormously. A bolt that travels mostly horizontally through the clouds creates longer, more sustained rumbles, because all parts of it are roughly the same distance from the ground. The sound arrives in a more compressed time frame, overlapping heavily and creating that deep, continuous roll that can last half a minute or more. A bolt that strikes more vertically, straight down from cloud to earth, creates shorter, punchier thunder. The difference in distance between the top and bottom of the bolt is more extreme, so the sound is more separated in time. You get distinct phases rather than one smooth rumble. Temperature plays a role too. Thunder travels faster through warm air than cold air. In a storm, you often have layers of different temperatures stacked on top of each other. A sound wave moving through these layers gets bent, refracted like light through a prism. Some frequencies get absorbed, while others get amplified. The bass notes, the really low rumbles, travel farther and penetrate deeper into buildings and bodies. This is why thunder sounds different, depending on where you are. If you're in a valley, the sound bounces off hillsides, extending the rumble even longer. If you're on a flat plain with nothing to interrupt the sound waves, you get cleaner, more distinct phases. If you're in a forest, the trees absorb the higher frequencies and let the bass through, making everything sound deeper and more mellow. The rolling thunder you hear isn't just one sound. It's dozens of sounds from dozens of sources, filtered through miles of atmosphere, shaped by terrain and temperature, arriving at your ears in a carefully staggered sequence that your brain weaves into something coherent and calming. It's organized chaos, and your nervous system has spent millions of years learning to find peace in it. The speed of sound through storms is where things get mathematical, but in a way that actually helps you relax. Because once you understand the numbers, thunder stops being random noise and becomes a measuring tool, a way to map the storm around you from the comfort of your bed. Sound moves through air at 767 miles per hour. That works out to about 1 mile every 5 seconds. This is slower in cold air faster in warm air, but 5 seconds per mile is close enough for practical purposes. So when you see lightning flash and start counting, you're doing real science. 1 Mississippi, 2 Mississippi, 3 Mississippi. 15 seconds means the strike was 3 miles away. 25 seconds means 5 miles. The math is simple enough to do half asleep. Light, meanwhile, travels so fast that for all practical purposes on Earth, you see lightning the instant it happens. The delay is unmeasurable to human perception. So, that gap between flash and thunder is purely about how far the sound has to travel. Its distance made audible. This creates something oddly comforting. You can track the storm without getting up, without looking at radar or checking your phone. Each flash gives you data. The storm is moving closer if the gap between flash and thunder shrinks. It's moving away if the gap grows. You're lying there in the dark, and your ears are telling you everything you need to know about what's happening miles above and around you. But here's where it gets even more interesting. Thunder doesn't just travel outward from the lightning strike. It travels through different layers of the atmosphere, each with its own temperature, pressure, and wind speed. These layers bend the sound waves, sometimes sending them back toward the ground after they've traveled upward, sometimes trapping them in channels that carry the sound much farther than it would normally go. On a warm summer night, you might hear thunder from a storm 20 miles away, far beyond the normal range. The sound waves hit a warm layer up high, get reflected back down, hit the ground, bounce up again, and keep going. It's like skipping stones, but with sound. The thunder arrives softer, more muffled, but it arrives nonetheless. In winter, when the air near the ground is often colder than the air above, sound waves bend upward and away. Thunder from a storm just a few miles off might be completely inaudible. The geometry of the atmosphere creates a sound shadow, a zone where the thunder simply doesn't penetrate. Humidity affects the speed too. Moist air is actually less dense than dry air because water vapor molecules are lighter than nitrogen and oxygen molecules. Sound moves slightly faster through humid air, which means thunder arrives fractionally sooner during heavy rain than it would on a dry day. The difference is small, maybe a few hundredths of a second per mile, but it exists. All of this means that thunder is never exactly the same twice. Every storm creates its own acoustic signature based on temperature, moisture, pressure, and the shape of the lightning itself. The rumble you're hearing tonight has never been heard before and will never be heard again. It's unique to this moment, this place, this particular arrangement of atmospheric conditions. And somehow, knowing that makes it easier to let go and simply listen. Now, let's address the fear directly, because understanding this changes everything. Thunder can't hurt you, not even a little bit. It's just sound, just pressure waves moving through air. And while it can be loud enough to startle you or wake you up, it has no physical power to cause harm. Lightning can hurt you. Lightning can kill you. But thunder is simply the announcement that lightning has already happened somewhere else. By the time you hear it, the electrical discharge is over. The energy has been spent, and all that's left is air molecules bumping into each other in a cascade that eventually reaches your eardrums. You're hearing an echo of violence, not the violence itself. The loudest thunder ever recorded measured about 120 decibels from a quarter mile away. That's loud, comparable to a rock concert or a chainsaw. But even at that volume, thunder isn't dangerous. It's not focused energy like a shockwave from an explosion. It's diffuse, spread out across the sky, weakening rapidly as it travels. By the time it reaches you inside a building, it's usually down to 60 or 70 decibels, about as loud as normal conversation. Your body knows this at some level. Your startle reflex might fire when a particularly close crack of thunder hits, but it's the same reflex that fires when someone slams a door or drops a book. It's not a fear response, it's just surprise. Within seconds, your heart rate settles back down. Your breathing normalizes. Unlike actual danger signals, thunder doesn't trigger the sustained fight or flight response that comes with real threats. Children often fear thunder until they learn this distinction. Parents say it's just noise, and eventually the child's brain accepts it. But adults can benefit from the same reframing. If you find yourself tensing up during storms, remind yourself that the thunder you're hearing is literally the sound of something that's already over. It can't reach backward in time to harm you. There's also no such thing as thunder without lightning, which means thunder can't sneak up on you. If you see the flash, you know sound is coming. If you don't see the flash, the storm is far enough away that you're in no danger from the lightning either. Thunder serves as an early warning system, not a threat in itself. Even the pressure wave that carries the sound is harmless. Yes, thunder is technically a shockwave, but it's so weak by the time it travels any distance that you'd never feel it as pressure. Only in the immediate vicinity of a lightning strike, within a few dozen feet, does the pressure wave have enough force to knock things over or break windows. And if you're that close, you have much bigger problems than the sound. This is why people throughout history have always been able to sleep through thunderstorms once they understood them. The sound is powerful, yes, but power without threat is just spectacle. It's fireworks, not warfare. Your ancestors learned to tell the difference, and that knowledge is still coded in your nervous system. When you consciously recognize that thunder is harmless, you're simply remembering something your body already knows. The storm can rage all night. The thunder can shake the windows and rattle the walls. And you can sleep through all of it, because deep down, you understand that this is nature's way of talking, not attacking. Thunder comes in varieties, and learning to recognize them is like learning to identify different instruments in an orchestra. Each type tells you something different about the storm, and each has its own quality that can help you relax. The sharp crack is what you hear from very close lightning, usually within a mile. The sound hasn't had time to spread out and soften. It's percussive, immediate, and over quickly. This is the thunder that startles people awake, but it's also the rarest type most people experience, because truly close strikes are uncommon unless you're in the middle of a severe storm. The long rumble is far more typical. This is thunder from lightning that's several miles away, where the sound has time to stretch and layer. It can last 30 seconds or more, rolling across the sky like a gentle wave. This is the sleep-inducing thunder, the kind that blends into white noise and actually helps your brain shut down for the night. Then there's the double boom, which happens when lightning strikes in two places almost simultaneously, or when a single bolt has two very distinct branches at different distances from you. You hear one crash, then a second one following close behind. Your brain recognizes these as separate events, even though they came from the same storm cell. It's like hearing a call and response, nature having a conversation with itself. Distant thunder is its own category. When storms are 10 or 15 miles away, the thunder becomes almost subsonic, more felt than heard. It's a pressure in your chest, a subtle vibration in the windows. The higher frequencies have all been absorbed by the atmosphere, leaving only the deepest bass notes. This is the thunder that puts people into the deepest sleep because it operates below the threshold of conscious attention. Heat lightning produces no thunder at all, at least none that reaches you. The lightning is so far away, sometimes 50 or 60 miles, that the sound dissipates completely before traveling that distance. You see the flashes illuminating distant clouds, but you hear only silence. It's eerily peaceful, like watching a movie with the sound turned off. Mountain thunder has its own character because of echoes. A single strike can produce 3 or 4 distinct rolls as the sound bounces off peaks and canyon walls. Each echo is softer than the last, creating a natural fade-out that can stretch for over a minute. People who live in mountainous areas often report that this is the most relaxing thunder because it has a musical quality, almost melodic in how it repeats and diminishes. Ocean thunder sounds different too. Over water, there's nothing to absorb or scatter the sound, so it carries farther and stays cleaner. You get longer, more sustained rumbles, without the choppy quality that terrain creates. Sailors have described thunder at sea as feeling more vast, more elemental, because the sound spreads across an open acoustic space with no interruption. Each type of thunder serves the same basic function, announcing that somewhere in the atmosphere, energy is being redistributed and balance is being restored. But the variety means that no two storms sound identical. Tonight's thunder might be all long rumbles. Tomorrow's might be sharp and percussive. Next week's might be so distant you barely notice it. And each variation offers its own pathway into sleep. Thunder doesn't just announce storms, it announces something cleaner happening in the air around you, a chemical reset that actually makes breathing easier and sleeping deeper. When lightning rips through the atmosphere, it does more than create sound. It breaks apart molecules. Oxygen molecules get split and recombined into ozone. Nitrogen bonds with oxygen in ways that don't normally happen. The electrical charge itself creates negative ions, tiny particles that flood into the air by the billions during every storm. These negative ions are the reason the air smells different after a thunderstorm. Fresh, clean, almost sweet. That smell has a name: petrichor. It comes partly from ozone, partly from oils that plants release, and partly from bacteria in the soil that get kicked up by raindrops. But the negative ions are what make your lungs feel like they're working better, like each breath is more satisfying than the one before. Scientists have studied this effect in laboratories. People exposed to air rich in negative ions report feeling more alert, less anxious, and more relaxed, all at the same time. Their sleep quality improves. Their mood stabilizes. The ions seem to affect serotonin levels in the brain, though the exact mechanism is still being researched. What's clear is that the effect is real and measurable. Thunderstorms produce more negative ions than almost any other natural phenomenon. Waterfalls create them too, which is why standing near a waterfall feels so refreshing. But a good thunderstorm can charge the air for miles around, turning your bedroom into something closer to the environment humans evolved in. Before we sealed ourselves into buildings with filtered, neutral air, the ions don't last long. Within hours, they bond with dust particles and other pollutants, becoming neutral again. But during and immediately after a storm, the concentration is high enough to have genuine physiological effects. Your body recognizes this charged air as something beneficial, something associated with rain and growth and the renewal of resources. This is part of why thunder is relaxing on a biological level. It's not just the sound, it's the total package. The sound tells you a storm is happening. The storm brings negative ions. The ions help you breathe better and think more clearly. Your nervous system connects all of these elements together and concludes that this is a good time to rest. Pollution gets scrubbed from the air during thunderstorms too. Rain physically pulls particulates down to the ground. The turbulence of the storm mixes the lower atmosphere, dispersing concentrated pockets of smog or allergens. Lightning converts some pollutants into less harmful compounds through chemical reactions. The air after a storm isn't just charged with ions. It's actually cleaner, easier on your lungs, less irritating to your sinuses. People with respiratory issues often report sleeping better during and after thunderstorms, assuming the storm doesn't create anxiety. The cleaner air, the higher humidity, the negative ions, they all work together to make breathing easier. And easier breathing means deeper sleep. So when you hear thunder, you're not just hearing sound, you're hearing the audible component of a process that's actively improving the air you're about to spend the next 8 hours breathing. The storm is resetting your environment, making it more conducive to rest, and your body knows this, even if your conscious mind doesn't. The reason people sleep better during thunderstorms isn't mysterious. It's a combination of factors that all push your body toward rest, and scientists have measured every single one of them. Start with white noise. Thunder creates a natural sound blanket that masks other noises that might wake you. The hum of traffic, a neighbor's dog, someone walking upstairs, all of these get drowned out by the rumbling. Your brain stops scanning for threats in the environment because the dominant sound is consistent and non-threatening. This lets your nervous system downshift into sleep mode. Then there's barometric pressure. Before and during a storm, air pressure drops. Your body notices this even though you're not consciously aware of it. Lower pressure means less oxygen in each breath, which makes you feel slightly drowsy. It's the same effect you get at high altitude, except much milder. Your body responds by slowing down, conserving energy, preparing to rest. Temperature drops too. Most thunderstorms bring cooler air, and cooler air is better for sleeping. Your core body temperature needs to drop by about 2 degrees Fahrenheit for you to fall asleep easily. A thunderstorm does half that work for you, pulling heat out of the air and out of your skin through evaporation and conduction. Your body doesn't have to work as hard to cool itself down. Humidity increases, which sounds like it would make things worse, but it actually helps. Dry air irritates your throat and nasal passages, causing micro-arousals throughout the night. Humid air keeps your airways moist and comfortable. The rain sound itself adds another layer of white noise, creating an acoustic environment that's remarkably similar to what sleep researchers use in laboratories when they want to help insomniacs. Light decreases. Storm clouds block the sun during the day and amplify darkness at night. This triggers your circadian rhythm to release melatonin earlier and in higher concentrations. Your brain interprets the darkness as a signal that it's time to sleep, even if it's only early evening. Thunder and lightning add drama to this darkness, but they don't disrupt the basic signal your body is receiving. There's also the psychological component. When a storm rolls in, you're given permission to stay inside, to do nothing, to simply rest. Society's expectations about productivity temporarily lift. No one expects you to go out in a thunderstorm. No one questions why you're lying down in the middle of the afternoon. The storm creates a guilt-free zone for rest. Your muscles relax more during storms too. The negative ions help, but there's also something about the sound vibrations themselves. Low-frequency sound, the kind that thunder produces, creates sympathetic vibrations in your body. Your chest cavity resonates slightly. Your bones conduct the sound. It's a subtle massage that you don't consciously notice, but that helps release muscle tension. All of these factors work together, creating optimal conditions for sleep. It's not one thing, it's everything at once. The sound, the pressure, the temperature, the ions, the darkness, the humidity, the permission to rest. Your body recognizes this specific combination as time to sleep because your ancestors spent millions of years sleeping through storms. The pattern is hardwired into your nervous system, and when thunder rumbles, that ancient program activates automatically. Thunder sounds different depending on where you are in the world, not because the physics changes, but because language and culture shape what we hear. The same rumble means different things to different people, and these interpretations reveal something beautiful about human perception. In English, we say thunder rumbles or rolls or crashes. These words focus on the acoustic qualities, the texture of the sound itself. But in Japanese, thunder is kaminari, which literally means peal of the gods. The word carries weight beyond just sound. It implies communication from something larger than human affairs. The Zulu word for thunder is ukuduma, which shares roots with words about making noise and causing commotion. It's active, energetic, but not necessarily threatening. Meanwhile, in Finnish, thunder is ökunen, derived from Ukko, the god of sky and weather. Even in modern secular Finland, the word carries echoes of that mythology. Arabic speakers use rad, which appears in the Quran as both a natural phenomenon and a reminder of divine power. The word suggests awe rather than fear. In Mandarin, li refers to thunder, but the character shows rain falling from clouds, grounding the sound in the visible weather that accompanies it. Some indigenous Australian languages have multiple words for different types of thunder, distinguishing between dry season thunder and wet season thunder, between thunder from storms that will bring heavy rain and thunder from storms that will pass quickly. The language maps directly onto survival knowledge, encoding information about what each type of thunder means for the community. In parts of West Africa, thunder is described as drums being played by ancestors or spirits. The rolling quality matches drum patterns used in traditional music, and people genuinely hear rhythm in the sound, where others might hear only noise. This isn't metaphor, it's actual auditory perception shaped by cultural context. When you grow up hearing complex polyrhythms in music, your brain becomes attuned to finding rhythm everywhere, including in thunder. Russian uses grom, which sounds harsh and percussive, matching the sharp quality of thunder in cold, dry air. Greek uses vronti, which has a softer, rounder sound, perhaps reflecting how thunder sounds different over the Mediterranean than over the Russian steppes. Hindi speakers say garaj, which sounds like what it describes, onomatopoeia that captures the third, rolling, guttural quality of distant thunder. Swahili uses radi, borrowed from Arabic, but adapted to local pronunciation, creating a bridge between linguistic traditions. The interesting thing isn't that languages have different words for thunder. That's obvious. The interesting thing is that people from different linguistic backgrounds report actually hearing thunder differently. English speakers hear crashes and booms. Japanese speakers hear more musical qualities. African languages with tonal systems report hearing pitch changes in thunder that other languages don't emphasize. This suggests that thunder, like all sound, is partly objective and partly constructed by our brains. The pressure waves are real and consistent, but what we make of those waves depends on our linguistic and cultural programming. Thunder becomes whatever our context tells us it should be. For some, it's gods bowling. For others, it's celestial drums. For still others, it's simply air moving. And all of these interpretations are equally valid because they all help people make sense of the same phenomenon. Beyond language and culture, thunder has rhythm. Real, measurable rhythm that follows patterns based on how lightning moves through the sky. And these patterns, when you learn to recognize them, become strangely predictable and comforting. A single lightning bolt creates a single burst of thunder that unfolds over time, as we've discussed. But storms don't produce just one bolt. They produce dozens, sometimes hundreds in an hour. And the spacing between these bolts isn't random. It follows the internal dynamics of the storm cell, creating a tempo that you can actually feel once you start paying attention. Most thunderstorms pulse. They build in intensity, reach a peak, then quiet down slightly before building again. This happens because of how convection works inside the storm. Warm air rises, cools, forms more cloud, gets pushed higher, eventually collapses back down. The cycle takes anywhere from 5 to 15 minutes, depending on the size and strength of the storm. Each cycle produces a cluster of lightning strikes, which means a cluster of thunder. You can hear this if you listen. The thunder comes in waves. 3 or 4 rumbles close together, then a pause, then another series. Your brain picks up on this pattern even if you're not consciously counting. It's similar to how ocean waves have sets, groups of larger waves, followed by calmer periods. The rhythm becomes predictable enough that your body can relax into it. Some storms maintain almost metronomic timing, a bolt every 30 seconds, like clockwork, for an hour straight. These are usually storms that have reached a stable configuration, where the energy input from rising air exactly matches the energy being released through lightning. The balance creates regularity, and regularity is soothing because it removes uncertainty. Other storms are more chaotic, with bursts of rapid-fire thunder followed by long silences. These are typically more intense storms, or storms that are transitioning between different phases. The irregularity can actually be more sleep-inducing for some people, because it prevents their brain from tracking the pattern consciously. Each rumble is a surprise, but a gentle one, keeping the mind engaged at just the surface level without demanding real attention. The rhythm also depends on the shape of the storm system. Linear storms, squall lines that stretch for hundreds of miles, produce more consistent thunder because you're basically hearing a conveyor belt of lightning moving past your location. The storm never really intensifies or weakens from your perspective. It just continues at the same level until it passes completely. Circular storms, like supercells, produce more variable thunder. As the storm rotates, different parts of it face your direction at different times. The thunder gets louder, then softer, then louder again. The rotation period might be 20 or 30 minutes, creating a slow oscillation in volume that feels almost like breathing. Clusters of smaller storms create complex, overlapping rhythms. You might have one storm to the north producing thunder every minute, and another to the west producing thunder every 45 seconds. The two patterns weave together, creating beats and syncopations that are genuinely musical if you have the ear for it. Your heartbeat naturally wants to synchronize with rhythms in your environment. This is called entrainment. When thunder establishes a rhythm, your heart rate subtly adjusts to match it. And since thunder is typically slower than your resting heart rate, this synchronization naturally slows you down, preparing your body for sleep. Thunder over open spaces transforms into something almost otherworldly. Over oceans, deserts, and prairies, where nothing interrupts the sound for miles, thunder reveals its purest form. On the ocean, thunder travels differently than it does over land. Water doesn't absorb sound the way soil and vegetation do. The surface is smooth and uniform, creating perfect conditions for sound waves to spread out in clean geometric patterns. Sailors describe ocean thunder as clearer, more bell-like, with distinct tones instead of the muddy rumble you get over forests or cities. The sound also carries farther over water. Thunder that would fade after 5 miles over land can reach 10 or 12 miles over the ocean. This happens because the temperature gradient is more stable over water. The air near the surface stays relatively consistent, creating acoustic channels that guide sound waves horizontally instead of scattering them in all directions. Over deserts, thunder takes on a different character. The hot, dry air conducts sound faster, and the lack of humidity means higher frequencies survive longer. Desert thunder is often described as sharper, more brittle, with a crackling quality that gets lost in more humid climates. The emptiness amplifies everything. There are no trees to dampen the sound, no buildings to create echoes, just open space, and raw acoustics. Prairies create their own effect. The flat grasslands let thunder roll for what seems like forever, spreading out in all directions with nothing to stop it. People who live on the Great Plains talk about thunder that lasts 2 minutes or more, a continuous rumble that feels less like individual strikes and more like one sustained note from the earth itself. In all of these environments, the absence of visual clutter makes the thunder more meditative. You can't see where the lightning struck. There are no landmarks to orient yourself. The thunder comes from everywhere and nowhere, creating a sense of being surrounded by something vast but intangible. Your brain stops trying to locate the source and just receives the sound as ambient presence. This is why open space thunder is particularly good for sleep. It doesn't demand that you figure anything out. Over land with trees and hills and buildings, your brain automatically tries to map the storm, to visualize where each strike happened based on the sound. But over empty space, that mapping is impossible. The thunder is just there, filling the air without requiring interpretation. The monotony helps too. Without echoes or reflections, each rumble sounds similar to the last. The variation that makes land thunder interesting becomes absent. Ocean thunder is ocean thunder. Desert thunder is desert thunder. The consistency creates a hypnotic quality, like a mantra repeated until it loses specific meaning and becomes pure vibration. People who live in these environments often report feeling more connected to weather than people in cluttered landscapes. When you can hear thunder from 30 miles away, when you can track a storm from horizon to horizon just by listening, the atmosphere becomes something you inhabit consciously rather than just move through. The openness also means you hear the storm's full life cycle. The first distant rumbles as it approaches, the crescendo as it passes overhead, the gradual fading as it moves away. This complete arc, from beginning to end, has its own narrative satisfaction. The storm tells a full story, and when it's finished, you can rest knowing the chapter is complete. The silence between thunderclaps is where peace actually lives, not in the sound itself, but in the quiet spaces that the sound creates by contrast. When thunder rumbles, your attention focuses on it automatically. Your brain orients toward the sound, tracking it, processing it, waiting for it to resolve. And then it does. The rumble fades. And in that moment of return to quiet, something shifts. The silence feels deeper than it did before the thunder started. Richer, more complete. This is a known phenomenon in acoustics and psychology. Sounds make the silences around them more noticeable. A single bell ringing in a quiet room draws your attention to the silence that follows. Thunder does the same thing, but on a larger scale, creating pockets of profound quiet between each rumble. Your nervous system responds to these quiet moments with relief. The thunder itself doesn't stress you, but it does activate your attention. When it stops, your body releases that attention. And the release feels good. It's a micro version of what happens when you finish a task or solve a problem. Brief engagement followed by rest. The longer the silence between thunderclaps, the deeper you can sink into it. A storm that produces thunder every 2 or 3 minutes gives you these extended periods of pure quiet. You have time to notice your breathing, to feel the weight of the blankets, to let your thoughts slow down and stop forming complete sentences. The thunder punctuates the silence, but doesn't dominate it. Meditation teachers use a similar technique with singing bowls. They strike the bowl, let it ring, then wait for the sound to fade completely before striking it again. The student learns to follow the sound into silence, using it as a pathway rather than a destination. Thunder works the same way without any effort on your part. The storm does the meditation for you. The silence also emphasizes the other sounds that are happening. Rain on the roof becomes more audible during the quiet periods. Wind in the trees, the slight creak of the house settling. These sounds are always there, but thunder frames them, makes them more perceptible by providing contrast. And all of these sounds together create a layered acoustic environment that's incredibly conducive to sleep. Some thunderstorms have almost no silence at all. The thunder rolls continuously, overlapping with itself, creating one sustained sound that doesn't stop. These storms can be sleep-inducing too, but in a different way. They function as white noise, masking everything else. But storms with clear silences between the rumbles are often more restful because they give your nervous system the chance to oscillate between engagement and release. The anticipation during silence is part of the effect too. You know more thunder is coming, but you don't know exactly when. This keeps your mind gently occupied without demanding real concentration. It's like waiting for the next wave at the beach. You're alert enough to notice when it arrives, but relaxed enough that the waiting is pleasant rather than anxious. Learning to rest in these silences is a skill, but one that comes naturally when you stop fighting the storm. Instead of wishing the thunder would go away, you start to appreciate the architecture of sound and silence it creates. The rumbles mark time. The quiet spaces let you exist between the markers. And in that rhythm, sleep becomes inevitable. Thunder can travel up to 12 miles under perfect conditions, and thinking about that journey helps put the sound into perspective. 12 miles is a long way for sound to go, and by the time it reaches you, it's been transformed by everything it passed through. Imagine a lightning bolt striking 12 miles away. The thunder leaves the strike site traveling at 767 miles per hour. In the first few seconds, it's loud enough to hurt your ears if you were standing there. Sharp, violent, the full force of that shockwave still intact. But immediately, the atmosphere starts working on it. The sound spreads out in a sphere, getting weaker as it goes. This follows the inverse square law, which means that doubling the distance makes the sound 4 times quieter, not twice. By the time the thunder has traveled 1 mile, it's already lost most of its punch. The sharp crack has started to soften into a rumble. As it continues, different frequencies get absorbed at different rates. High frequencies disappear first, filtered out by humidity and scattered by air molecules. The sound loses its bright edges, its crispness. What remains are the lower frequencies, the bass notes that can travel farther because they have more energy and longer wavelengths. Temperature layers bend the sound waves, sometimes sending them up into the atmosphere where they dissipate, sometimes reflecting them back toward the ground. Wind can push the sound in one direction, creating zones where thunder is louder or softer than it should be, based on distance alone. Every variable in the atmosphere between you and the lightning strike affects what you eventually hear. By mile 6 or 7, the thunder has become something almost unrecognizable compared to what it was at the source. It's soft, low, more of a presence than a distinct sound. The individual shock that created it has been smoothed out by distance into something gentle and continuous. At 10 miles, you're hearing only the deepest tones. The rumble feels more than heard, a vibration in your chest rather than a clear sound in your ears. Some people can't detect thunder at this distance at all. Their hearing doesn't extend low enough into the bass frequencies. Others feel it as an uneasy sense that something is happening without being able to identify what. At 12 miles, under ideal conditions, with perfect humidity and temperature, the very last traces of thunder can still reach you. It's barely there, a whisper of pressure variation in the air. But the fact that it exists at all is remarkable. Sound that started as a violent explosion has traveled the length of a small city, crossing forests and fields and neighborhoods, arriving at your window so gentle it barely disturbs the air. This long journey is why distant thunder is so peaceful. You're hearing violence that has been completely defanged by distance. Whatever threat the lightning posed is miles away and long over. What reaches you is just the echo, softened and made safe by the simple physics of sound propagation. When you hear thunder that's clearly distant, you're hearing proof that you're safe. The storm is far enough away that you have nothing to worry about, and your body understands this calculation instinctively, allowing you to relax fully into the sound, because the sound itself confirms there's no danger. Thunder stays in memory longer and more vividly than almost any other weather phenomenon. Ask someone about a specific thunderstorm from their childhood, and they can often describe it in detail. The smell of the air, the sound of the rain, exactly where they were sitting. These memories are powerful because they connect to feelings of safety and comfort that run deep. For most people, childhood thunderstorms meant staying inside. School might get cancelled. Outdoor activities got postponed. Parents would gather everyone into the living room or a central part of the house. The normal rules relaxed. You could build blanket forts, read books all afternoon, drink hot chocolate even though it wasn't that cold. Thunder created permission for slowness and togetherness. These associations don't disappear as you age. They get encoded into your nervous system as patterns. Thunder equals safety. Thunder equals rest. Thunder equals being cared for. When you hear thunder as an adult, those old neural pathways light up. Your brain remembers what thunder meant before you had responsibilities, before you had to worry about commutes, or leaking roofs, or cancelled appointments. The predictability of thunderstorms helps cement these memories. Storms have beginnings, middles, and ends. They arrive, they peak, they pass. This narrative structure makes them easier to remember than, say, a cloudy day or steady rain. Your brain likes stories, and thunderstorms are inherently story-shaped. Regional memories play a role too. If you grew up somewhere with frequent summer thunderstorms, the sound triggers memories of specific seasons. The end of hot afternoons, the smell of grass and wet concrete, the way light looked filtering through storm clouds. These sensory details layer together, making thunder a portal to entire periods of your life. For people who grew up in climates without much thunder, even 1 or 2 memorable storms can create strong associations. The rarity makes them stand out. That one time the power went out and your family played board games by candlelight. The camping trip when thunder echoed through the mountains all night. These isolated memories become touchstones, moments of unusual weather that marked unusual circumstances. The social aspect reinforces the comfort. Thunderstorms are one of the few times when being inside with others feels natural and justified. No one questions why you're staying in. No one suggests you should be doing something more productive. The storm creates a bubble outside of normal time where just existing together is enough. This is why recordings of thunderstorms can help people sleep, but they're not quite the same as real thunder. The recordings have the sound, but they lack the full context. The drop in pressure, the change in light, the smell of ozone, the knowledge that something real is happening outside. Real thunder activates more complete memory patterns because it includes all the sensory elements that were present in those childhood experiences. Your body remembers being small and safe while thunder rolled overhead. It remembers the feeling of being protected by walls and roof and the presence of people who cared about you. These aren't conscious thoughts. They're deeper than that, wired into your stress response system as examples of situations where you can fully relax. When thunder rumbles tonight, part of what you're hearing is every other thunderstorm you've ever experienced. The sound carries all those memories with it, all that accumulated proof that thunder means you're safe, you're sheltered, and you can rest. Lightning comes in colors, and each color creates a different quality of thunder. Most people only notice white or yellow lightning, but storms produce an entire spectrum, and the color tells you something about where the lightning is and what it's moving through. Blue lightning happens when a bolt passes through hail or ice crystals. The ice scatters the light in specific ways, filtering out the warmer colors and letting blue through. This type of lightning usually produces sharper, more brittle-sounding thunder because it happens in colder parts of the atmosphere where sound travels differently. The thunder has a higher pitch, less of the deep rumble you get from warm air lightning. Red lightning is rare and happens when bolts travel through rain or high-altitude dust. The particles scatter short wavelengths and let the longer red wavelengths pass. This lightning often produces thunder that sounds more distant than it actually is, because the same atmospheric conditions that create the red color also affect how sound propagates. The thunder comes out muffled, softened, almost gentle. Pink lightning combines both effects, passing through both rain and ice. It's most common in severe storms with complex vertical structure. The thunder from pink lightning tends to have a wider frequency range, more complexity in its tone. You can sometimes hear distinct layers in it, high notes and low notes separated rather than blended. Green lightning appears in storms with large amounts of hail. The color comes from light passing through ice that's mixed with dust or pollen. Tornado-producing storms sometimes show green lightning because of the specific atmospheric conditions that create both phenomena. The thunder associated with green lightning is often described as deeper and more continuous because these storms have such powerful updrafts that lightning is nearly constant. Orange lightning happens during sunset or sunrise, when the sun's light mixes with the lightning's own light. The color is atmospheric, not inherent to the bolt itself, but it still affects perception. People report orange lightning thunder as sounding warmer if sound can have temperature. This is likely psychological, the color influencing how the sound is processed. White lightning, the most common type, is just lightning with no significant filtering. The bolt is producing all wavelengths equally, and none are being preferentially absorbed or scattered. White lightning produces the standard thunder sound most people know, with the full spectrum of frequencies intact. Purple or violet lightning happens at very high altitudes, above most of the atmosphere's dust and moisture. It's rare to see from the ground, but pilots and mountain climbers report it occasionally. The thunder from high-altitude lightning often doesn't reach the ground at all, dissipating before it travels that far through the thin air. The interesting thing is that your brain connects color and sound even when there's no logical reason for the connection. Studies show that people consistently describe thunder as sounding different depending on the color of lightning they saw, even when played identical audio recordings. Blue lightning thunder sounds colder. Red lightning thunder sounds softer. The visual information shapes the auditory experience. This means that no two thunderstorms sound exactly the same, even if the physics are identical. The colors you see, the expectations you bring, the memories you associate with different types of storms, they all blend together to create your experience of the sound. Thunder isn't just heard, it's felt. Close lightning creates vibrations that travel through the ground and through buildings, reaching your body directly without needing your ears at all. When lightning strikes within a mile or so, the shockwave hits the ground with enough force to create seismic vibrations. These are tiny, barely measurable tremors, but they're real. Seismographs can detect them, and so can your body, though you might not consciously realize what you're feeling. The sensation is subtle, a slight pressure in your chest, a faint tremor in your bones. If you're lying down, you might feel it through the mattress, a vibration so brief you could easily mistake it for imagination. But it's physical. Sound waves at very low frequencies, below the range of human hearing, still carry energy. That energy moves through solid materials more efficiently than through air. This is why thunder feels more powerful when you're inside a building than when you're outside. The building collects the vibrations, channels them, amplifies certain frequencies. The walls and floor become resonators, conducting the sound through their structure and into your body. You're not just hearing the storm, you're connected to it physically. Some people find this unsettling. The idea that they can feel thunder, that the sound is literally moving through their skeleton, makes the storm seem more invasive. But others find it grounding. The vibration is proof that you're not separate from the weather. You're part of the same physical system. The thunder moving through you is the same thunder moving through the trees and the soil and the stones. Very low frequency sound, the kind below 20 Hz, can affect your body without you being aware of it. Your heart rate can synchronize with it. Your breathing can slow to match its rhythm. This happens unconsciously, your nervous system responding to pressure waves that never register as sound in your conscious mind. Thunder contains a lot of energy in these low frequencies. The deep bass rumbles you hear are just the upper edge of the spectrum. Below that are infrasonic waves that you feel more than hear. These waves can travel for miles through the ground, arriving before or after the audible thunder, depending on the geology between you and the strike. Research on infrasound and sleep shows that very low frequencies can actually promote deeper sleep stages. They seem to help the brain transition from lighter to deeper sleep by providing a gentle, consistent stimulus that keeps the nervous system occupied without demanding attention. Thunder naturally produces these frequencies as a byproduct of being such a massive displacement of air. The vibrations also create a sense of enclosure. When you can feel the thunder as well as hear it, the storm becomes three-dimensional, surrounding you rather than just existing somewhere outside. This can be comforting in the same way that wearing headphones creates a bubble of sound that feels protective. Your body interprets these vibrations as confirmation that you're sheltered. If you can feel the thunder through the building, it means the building is solid enough to conduct the vibrations, which means it's solid enough to protect you. The sensation becomes proof of safety rather than a sign of danger. So, when the next rumble makes your chest hum slightly, or when you feel that faint tremor through the floor, remember that you're experiencing thunder in its fullest form. Mountains and valleys transform thunder into something extraordinary through echoes that can last for minutes. The geography creates natural amplifiers and delay systems that turn a single strike into a symphony. When lightning hits in mountainous terrain, the thunder spreads out in all directions like usual. But instead of dispersing into open air, it hits rock faces. Hard surfaces reflect sound waves efficiently, bouncing them back across the valley. Each mountain face acts as a mirror for sound, creating copies of the original thunder that arrive at your ears seconds or minutes later. A single bolt might produce 6 or 7 distinct echoes, each one softer than the last. You hear the original thunder, sharp and clear. Then, a second later, the first echo arrives from the nearest peak, then another from a more distant ridge, then another from the far side of the valley. The sound builds and overlaps, creating sustained rumbles that far outlast what the lightning itself produced. Canyon systems create even more complex effects. Thunder can bounce back and forth between parallel walls dozens of times before finally dissipating. Each reflection loses some energy, but in deep canyons, the geometry is so favorable that echoes can persist for over a minute. People camping in slot canyons have described thunder that sounds like it's rolling up and down the canyon repeatedly, searching for a way out. The spacing between echoes depends on the distances involved. If valley walls are a mile apart, the echo takes about 10 seconds to make the round trip. Wider valleys produce longer delays. Narrower valleys create faster repetitions that blend together into continuous sound. The shape of the valley matters too. U-shaped glacial valleys reflect sound differently than V-shaped river valleys. Mountain thunder has been part of mythology worldwide because of these acoustic properties. The sustained rumbles sound less like weather and more like something deliberate, something conscious. Ancient cultures heard gods speaking, spirits moving, cosmic forces at work. Even today, with scientific understanding, mountain thunder feels more alive than plains thunder. The echoes also help with distance calculation. If you hear thunder and then hear it again from behind you, a few seconds later, you know. The sound bounced off something and returned. You can mentally map the landscape just by listening, figuring out where the major reflective surfaces are based on when their echoes arrive. Valleys channel sound in other ways too. Thunder tends to flow downhill, following the valley floor like water. A storm at the head of a valley can be heard clearly 20 miles away at the mouth, even though the same storm would be inaudible at 20 miles across flat terrain. The valley walls guide the sound, keeping it concentrated instead of letting it spread out spherically. Forests in mountain valleys absorb some frequencies while letting others through. You end up with thunder that's been acoustically filtered, stripped of certain tones, leaving only the frequencies that the landscape naturally amplifies. Each mountain range has its own signature sound, its own way of shaping thunder into something unique. For people trying to sleep in these environments, the extended thunder can be deeply hypnotic. The original sound triggers your attention, but then the echoes give you something to follow, to trace through the darkness. Your mind stays gently engaged, tracking each repetition as it fades. And somewhere in that process, you slip into sleep without noticing the transition. There's mathematics hidden in thunder, elegant patterns in how the sound weakens with distance. And understanding these patterns reveals something peaceful about the universe, following simple, predictable rules, even in something as chaotic as a storm. The inverse square law governs how thunder fades. When sound travels twice as far, it doesn't just get half as loud. It gets 1/4 as loud, triple the distance, and it becomes 1/9 as loud. The relationship is exponential, which means thunder weakens rapidly as it moves away from its source. This creates a natural safety buffer. Lightning that's close enough to be dangerous is also loud enough that you can't possibly miss it. By the time thunder has softened into something gentle and sleep-inducing, the lightning that created it is far enough away that you're in no danger. The mathematics ensures that soothing thunder equals distant lightning. The speed of sound also follows predictable formulas based on temperature. For every degree Celsius increase in air temperature, sound travels about 0.6 meters per second faster. This means you can actually calculate the temperature of the air between you and the lightning strike if you know the distance and time delay. The thunder carries information encoded in its timing. Frequency decay follows patterns too. Higher frequencies lose energy faster than lower frequencies when traveling through air. This happens because high-frequency sound waves interact with air molecules more often, transferring energy with each interaction. The relationship is mathematical and consistent. Thunder 10 miles away has lost nearly all frequencies above 500 Hz. Thunder 15 miles away loses everything above 300 Hz. This natural filtering is why distant thunder sounds so different from close thunder. It's not just quieter, it's been stripped of all its sharp edges by the predictable physics of sound absorption. The mathematics of the atmosphere acts as an equalizer, removing high tones and leaving only bass. Reflection and refraction follow rules too. When sound waves hit a boundary between air masses of different temperatures, a specific percentage gets reflected and the rest passes through. The angle of reflection equals the angle of incidence, just like light bouncing off a mirror. Temperature gradients bend sound waves. According to Snell's law, the same equation that describes how lenses focus light. All of this means that thunder, despite seeming random and chaotic, is actually following precise mathematical laws at every moment. The rumble you hear is the result of countless small calculations happening automatically in the physics of the atmosphere. Sound pressure, air density, molecular collision rates, thermal energy transfer, all of it proceeding according to equations that scientists have understood for decades. There's something deeply restful about this. The universe isn't random. Even in a violent thunderstorm, nature follows rules. The same rules that govern laboratory experiments govern the sound reaching your ears right now. You can trust the patterns because the patterns are fundamental to how reality works. When you hear thunder getting softer, you know with mathematical certainty that the storm is moving away. When you hear the deep bass rumble of distant thunder, you know the high frequencies have been filtered out by distance according to predictable absorption rates. The sound tells you exactly what's happening, and the message is always consistent because it's based on physics that doesn't change. This reliability, this predictability, makes thunder safe to ignore. Your brain can trust that the patterns mean what they've always meant. Thunder sounds different at night, and the difference is measurable. When the sun sets, the entire acoustic environment shifts, making nighttime thunder deeper, more intimate, and more conducive to sleep. During the day, the sun heats the ground, which heats the air near the surface. This creates turbulence, rising currents of warm air mixing with cooler air above. Sound waves traveling through this turbulent layer get scattered in random directions. Thunder. During the day is choppy, broken up, less focused. At night, the ground cools. The air near the surface becomes cooler than the air above it, creating a stable temperature inversion. Sound waves prefer to travel through this stable layer rather than scattering upward. They get channeled along the temperature boundary, traveling farther horizontally while staying close to the ground. This is why you can hear distant thunder more clearly at night. A storm 20 miles away might be completely inaudible at noon, but perfectly clear at midnight. The night atmosphere acts as a waveguide, directing sound toward you instead of dispersing it in all directions. The frequency balance changes too. Nighttime cooling affects different frequencies differently. Lower frequencies travel even better through cool air than through warm air, while higher frequencies get absorbed more quickly. Night thunder skews deeper into the bass range, becoming more of a rumble and less of a crack. Humidity rises at night as temperatures drop, and humid air conducts sound slightly better than dry air. The moisture in the air, rather than dampening the sound, actually helps it travel by making the air denser and more uniform. Each water molecule in the air is another pathway for pressure waves to propagate. Background noise decreases dramatically at night. Traffic thins. People stop moving around. Even birds and insects quiet down. In this silence, thunder stands out more clearly. But it's not just about contrast. The absence of daytime sounds means your auditory cortex isn't competing to process multiple inputs. Thunder gets your full attention without demanding it. Your brain processes sound differently at night too. As you approach sleep, your auditory threshold changes. You become less sensitive to sudden sharp sounds and more attuned to sustained, low-frequency sounds. This is an evolutionary adaptation. Deep sounds mean large things, potentially dangerous things, worth monitoring even during sleep. But the sustained rumble of thunder, once your brain categorizes it as non-threatening, becomes part of the safe soundscape rather than an alarm signal. The darkness amplifies the acoustic experience by removing visual information. During the day, you can see where the storm is, watch the clouds move, track the lightning visually. At night, you're forced to rely entirely on sound. This heightens your sensitivity to the audio, making the thunder feel more present, more encompassing. Storms at night also feel slower. Without visual cues about the storm's movement, you lose the sense of speed. The thunder seems to linger longer, each rumble hanging in the air without the distraction of seeing the next lightning flash approach. Time stretches out, and in that stretched time, sleep arrives more easily. The combination of all these factors makes nighttime thunder ideal for rest. The deeper tones, the clearer transmission, the quieter background, the altered perception, they all work together to create an acoustic environment that your body recognizes as perfect for sleep. So here we are at the end, back where we started, listening to thunder. But now you understand what you're hearing. Not just noise, but a complete system designed by physics to help you rest. Thunder combines everything your body needs for sleep. The white noise that masks disruptions, the low frequencies that resonate in your chest and slow your heart rate, the negative ions that clean the air and ease your breathing, the predictable patterns that let your mind relax without shutting down completely, the childhood memories of safety and shelter, the proof, delivered every few seconds, that you're far enough from danger to stop being vigilant. It's not one thing that makes thunder relaxing, it's everything working together. The sound, the pressure, the chemistry, the associations, the mathematics. Nature has spent billions of years perfecting storms, and humans have spent millions of years learning to sleep through them. You're the result of that long optimization process. Your nervous system knows exactly what to do with thunder. When the next storm rolls in, you don't have to fight it or fear it. You can let it do what it's designed to do. The thunder will mark time, creating a rhythm that your body can synchronize with. The sound will fill the space around you, giving your attention something to rest on without demanding real focus. The silence between rumbles will deepen, offering moments of pure quiet that feel richer because the sound frames them. You can track the storm if you want, counting seconds between lightning and thunder, mapping the cells as they move across the sky. Or you can stop tracking entirely and just let the sound wash over you, trusting that if anything required your attention, the thunder would sound different. Close thunder is unmistakable. Distant thunder is permission to sleep. The storm will pass eventually. All storms do. But while it's here, while the thunder rolls and the rain falls and the air fills with ions, you're experiencing something ancient and automatic. Your body remembers this. Every cell in you has been trained by evolution to recognize thunder as the sound of nature maintaining itself. balancing itself, continuing the cycles that make life possible. And in that recognition, in that deep cellular understanding, there's nothing to do but rest. If you've enjoyed this journey into the peaceful science of thunder, please like and subscribe to Simple Sleepy Science. We'll be here tomorrow night with another exploration into the natural world, another invitation to wonder and rest. Every night, a new topic. Every night, a new pathway into sleep. We're building a community of curious minds who find peace in understanding, who sleep better when they know how the world works. The thunder will keep rumbling. The storms will keep coming. Sleep well. The storm has you covered.